Hello everyone and welcome back. So today we are going to learn recursive tree method. In recursive tree method, recursive relation is converted into tree, and after that work done at each node is calculated, which is then added for each node to get final value. So why we are going to use recursive tree method? Why we are not using substitution method? Because in substitution method we cannot apply it for every function. In some case the function get too complex to apply substitution method, so in that case we use recursive tree method. So suppose in this example this function have only one function call, which is t n minus 1. In that case it is easier to apply substitution method, but when the function get complex, so in the second example there are two functions called, one is t n minus 1, another is t n minus 2. So here more than one function call become too complex to solve. So here we use recursive tree method in that case. A recursive function generally have two part. So let's take a recursive relation which is tn equal to tn minus 1 plus tn minus 2 plus n. So it's have two part. So first part is the function call, where we call the function again and again with different values, and the other part is the variable part. So this is the actual time consumed at each function call. So in this example what's happening, so for tn, when the function tn is called, then inside it's calling two other function, and apart from calling the two functions there is some extra work being done in that function call, which is consuming n unit of time. So here it is the work done at each function call, which is n. Let's see what I meant by an example. So here we have a function a, and it have a termination condition if n equal to 1, return 1. So this will consume a total of constant time, so we can write it as c as constant, and the else condition which will call the function again and again. So it have a loop inside it, so it is running from 1 to n. So this loop will run a total of n time, so we can say it is consuming n unit of time. And the return statement, which is the actual recursive statement, so it's calling the function two times, one for n minus 1 and one for n minus 2. So for every function call this loop will run. So this will be the work done at each function call. So whether you run this loop for any value, this loop will run every time. So it is the work done at each function call. And if we do not have this loop, then we can say constant unit of time is consumed. So the function will become tn minus 1 plus tn minus 2 plus c. So here constant will be the work done at each function call if there was no loop. Let's solve an example to understand recursive tree method. So here we have our recursive function, which is tn equal to tn minus 1 plus tn minus 2 plus c. So here c is the work done at every function call. So let's write it here. We will form a tree using this recursive relation. So we have tn, and tn is called two times, one for tn minus 1, other for tn minus 2. Similarly this will be called further, one for n minus 2 and for n minus 3. This will be called for n minus 3 and this will be called for n minus 4. So this will go until k times. So both sides it will run k times, and at the end of k time it will become n minus k. And here you can see there is a pattern which is which we simplify, it is n minus 2 into 1, this is n minus 2 into 2. So here it will become n minus 2 into k, and at some point of time, let's say after k times, we get this terminated. So n minus k got terminated, and the termination condition, let's assume there is some constant termination condition when say t0, for t0 it got terminated. So when n minus k becomes 0, then it will get terminated. So we can find the value of n and k. So we can find the value of k here, k will become equal to n. So this will run a total n times. So you can see the depth of the tree. So this will be equal to n. And let's see the other side. So here we have n minus 2k. So at some point in time this will also become equal to 0. So n minus 2k will become equal to 0, and we can get the value of k from here, which will be equal to n by 2. So we can say this length is n by 2. So when we are doing minus 1 every time, then the length will become n. So max function call in that will be n. And when we are doing minus 2 every time, then the length will become n by 2. So n by 2 functions calls there. And this tree which is in between, this will run accordingly. So the largest length will be n and the shortest length will be n by 2. Let's see how we got depth of tree as n one side and n by 2 as the other side. So suppose we have a number n and we do minus 1 every time. So we will do minus 1 minus 1. So we have to do a minus 1 n times to make it 0. So here we get n. So we have to run this n minus time to get the 0. So that's why the depth of the tree one side is n. And if we do n minus 2 every time, minus 2 minus v, so it will take a total of n by 2 times to make it 0. So that's why on the other side we have n by 2 as the depth. Now let's see how much time this recursive relation will consume. So to find the time complexity, so for each function call it is consuming c amount of time, which is constant. So let's take a look at the tree. So at first level we have only one function call, so it will consume c unit of time. On the second level it have two function calls, so it will consume 2c amount of time. And on third level it have four function call, so it will consume 4c amount of time. And on fourth level there will be 8 function calls, so there will be 8c amount of time consumed. So you can see a pattern here. C can be written as 2 raised to power 0c, this can be written as 2 raised to power 1c, this can be written as 2 raised to power 2c, and it can be written as 2 raised to the power 3c. So you can see at first level there is 2 raised to power 0c, at second level 2 raised to 1c, at third level 2 raised to power 2c, and at fourth level it is 2 raised to power 3c. And this function will run up till k times, and after k time it got terminated. So after k times the function will have, we can say, 2 raised to the power kc function calls, and it will consume 2 raised to the power kc amount of time. So if we sum of these values, so 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, if we sum up these value, so we have 2 raised to power 1c plus 2 raised to power 2c plus 2 raised to power 3c, and it will go up to 2 raised to the power kc. So here we also have 2 raised to power 0c also, so we can write it here. So if you can see, this series is an increasing GP series, and for increasing GP series the last term which is in the GP series is the answer. So all these terms that come before the last term, they are very small if we compare it to the last term for a large number. So the answer will be big of 2k, and we can substitute the value of k here. So we have found out that the value of k will be n, so the final answer will be big of 2n, and this can be written as theta also. So this will be our final answer. If you take a closer look at the tree, you can see at one time the number of levels are n, and on the other side the numbers of levels are n by 2. So these are not even both sides. So if we draw the graph one more time, we can see, so here will be our tn, and this side will we have n levels, so the depth will be n, and on the other side we have n by 2 levels. So this is the way the graph is looking right now. So we cannot say that at the nth level there are a total of 2 raised to the power n functions calls. So the function calls will be between 2 raised to the power n and 2 raised to the power n by 2 in the nth level. So there are not 2 raised to the power n function calls. So we can write it as that the upper bound for this function call we can take it 2 raised to the power n, and the lower bound we can take as 2 raised to the power n by 2. But the final answer we will always take the worst case, so that will be 2 raised to the power n. Let's see one more example. So here we have our recurrence relation, and which is Tn. So we have Tn equal to Tn by 2 plus Tn by 3 plus C. So here you can see there are two function call inside a function call. So it is passing the value as n by 2 and n by 3. So it's dividing in n by 2 and dividing in n by 3. And the time consumed for each function call is C unit, which is constant unit. First we will draw the tree for this reconciliation, so let's do it. So we have our Tn here, and this is divided into two parts. One is Tn by 2 and another part is n by 3. So the function is called again, so this side it will be n by 2 square and it will be n by 2 into 3. Here it will have n by 2 into 3, and on the other side it will have n by 3 square. So this will keep on continue for k times both side, and after k times this side will become n by 2 raised to the power k, and this will become n by 3 raised to the power k. So we say that at k time it will got terminated, and the value of n by 2 raised to the power k will become equal to 0. So we can find the value of k from here. So n will equal to 2 raised to the power k, and the value of k will be, we take both log both sides, so it will become log n. So this will be the value of k, and this side if we see the value of k will become log n. So this will be a base 3 log n, and this will be a base 2 log n. So when the base is small, that value is big, so the bigger value will be log base 2n and the smaller value will be log base 3n. Now let's see what will be the time complexity of this. So this side it will have log base 2 n levels, and on the other side the graph will have, the tree will have log base 3 n levels. So if you look at this recursive relation, so it is consuming C unit of time at every function call. So for first function call it is only single, so it will have consume C unit of time. For second level there are two function calls, so 2 C unit of time will be consumed. At third level there are 4 function calls, so 4 C amount of time will be consumed, and at eighth level there will be 8 function calls, so 8 C amount of time will be consumed. And if we simplify this can be written as 2h power 0 C, this can be written as 2h power 1 C, 4 can be written as 2h power 2 C, and 8 can be written as 2 raised to the power 3 C. And we can follow the pattern for k level also. So at kth level there will be 2 raised to the power kc function calls, and if we sum up all these value, So we have 2 raised to the power 0c plus 2 raised to the power 1c plus 2 raised to the power 2c. So this will go to 2 raised to the power kc. And as you know that it is an increasing GP series, and an increasing GP series, the last term is the answer. So this will be the major portion of the series. So we have 2k as the final answer, and we can replace the value of k here. So k is 2h to the power log 2n, and this can be written as n. So the final answer will be big O of n.